Over a single year, 3 separate teams of physicists published results that appear to break the standard models of their respective fields. In ultra-pure graphene, researchers observed electrons moving with a collective viscosity. Instead of scattering like individual particles, they formed whirlpools, flowing like a liquid. Simultaneously, a quantum computer produced a state using only 216 photons. To describe this configuration using our current classical data structures would require 10 to the power of 170 bits, a number that exceeds the storage capacity of every server on the planet. In a third laboratory, physicists confirmed the qutrit, an irreducible 3-valued logic state. This quantum coherence cannot be decomposed into binary components, operating entirely outside the 0 and 1 logic of modern computing. These discoveries represent a localized failure of our physical models across 3 different disciplines. The scientific community is currently attempting to reconcile these events through traditional debates, arguing whether the universe is fundamentally discrete or continuous, or if reality is composed of particles or fluids. This image from a bubble chamber captures the rigid, linear paths that defined 20th century particle physics. These models work within specific limits, but they become intractable when applied to these new, high-interaction states. The electron whirlpools, the massive photon data load, and the 3-valued logic state all point toward the same structural limit. The conflict originates in the fixed mathematical frameworks we use to observe these phenomena. A framework called the mechanics of all, or TMOA, provides a mathematical architecture to address this structural limit. This is the base field equation. It introduces sigma, a dynamic scale dimension where physics propagates just like space. Its primary tool, the pi projection operator, dictates the underlying substrate remains static, while representation changes based on observation scale, minimizing computational cost and error. This removes the idea of a privileged or true level of reality. Every observation is a projection at a specific scale. When applied to graphene, the operator shows that the electrons didn't change their nature. At a high enough interaction density, a fluid basis becomes mathematically cheaper than a particle drift basis. The representation switched because the interaction hierarchy shifted. In the case of the 216 photons, the 10 to the 170th bit count is a property of the projection, not the light. Using a classical bit basis to describe a quantum state creates an exponential explosion in computational cost. For the qutrit, the operator demonstrates that the cardinality of our logic, the number of possible states, is a function of the observation window. Applying a binary basis to a 3-valued state simply discards physical structure. These 3 results share a single cause, a mathematical description applied outside the regime where it is most efficient. The projection operator provides a unified way to calculate these transitions. This framework relies on substrate invariance. The territory does not change under observation, only our representations do. It also requires basis relativity. Forcing any mathematical model outside of its natural measurement scale results in either a loss of information or a massive spike in computational complexity. Physics must move past the search for a single universal model and instead focus on the operators that govern how these models transition. The ultimate implication is that there is no fundamental floor to reality. Instead, we find an infinite nesting of scales. Every structure we observe decomposes into finer components, and every component composes into larger systems, without termination. The debates between particle and wave, or classical and quantum, are now secondary to the study of scale itself. By utilizing the base field equation, we stop treating different scales of physics as conflicting truths and begin understanding the mechanics of the entire system.